So we're going to take a look at partial fraction decomposition. And this is something that really is going to be helpful in calculus. And what you're going to have some rational functions that they may not appear integrable. We'll get to integrals in calculus. It's a modification of a function, a special modification that lets you find the area underneath a function. So you have some function here. You can find the area underneath this function for, well, there's different reasons. For example, if this function here represented force, say this is a force function, and this is distance d, and let's say we have point A, point B. So what could be happening here is you're starting at point A, and you're pushing some cart. There might be some kind of friction or something you have to push against point B. And the force you exert on this cart could be described as this. And so we're just interested, well, how much work did you do? Because work is defined as force times distance. It's capital D. So the problem is this area here is going to represent the work. But the problem we're going to run into is that the force here, well, it's changing all the time. It's sort of an irregular shape. So to find the area underneath this curve, get the area that represents the work, we got to use this integral. Let's just find the area of these irregular shapes. Well, to do that, you use this calculus modification. Sort of, it's an operator. It modifies your function. And what it does is you can use this function to find these areas. Now, there's certain rules for modifying these functions, and some functions they really don't seem like you can modify them. Now, you can use numerical approximations using techniques from calculus, but sometimes there are some tricks you can use to do this, and one of the tricks is partial fraction decomposition. It's a trick that we use with rational functions when they don't lend themselves to being integrated. So let me show you how this works. Now I'm going to use sort of a trick for multiplying these or adding these together. And the trick is this. Let's say we have two fractions, A over B, C over D, and we're adding or subtracting them. What we could do is multiply across for a denominator, cross multiply, whatever sign we have here or operator, we bring that down. Then we cross multiply again. So basically we do this, this, and that. It's just sort of a shortcut for adding, subtracting rational functions or fractions. It'll work with fractions as well. You usually have to do some reducing at the end. So I'm going to use that just to save some time. And it's a neat trick to have too. So if we add these two rational functions, x minus 1, x plus 2, again, multiplying across, cross multiply, cross multiply, and let's see, make sure you can see this. Sometimes it gets a little bright. There we go. And if we do our distributions here, combine like terms, and we're going to get something like this. We're going to get 7x plus 2 over x minus 1, x plus 2. So what we're interested in is if you take this function, say you're in calculus 1, or if you could FOIL the bottom here, they're not going to get anything that cancels. There's no factors here that cancels with this. This is a factor, this is a factor, this is a factor. They don't cancel. And so you're going to be in a little bit of hurt in calculus 1 if you try to come up with a U substitution for this. So there's another way you can go about this, and it's to use partial fraction decomposition. And what we want to do is look at this backwards. 7x plus 2, x minus 1, x plus 2 is 3, x minus 1, x plus 2. It'll turn out in calculus this is fairly easy to integrate in this form. So it's going to be easier than this. And what you can do is, well, that's what you want to do. You're going to use a natural log ultimately for this integral, but that's for another time. But we want to break this down to the sum of two rational functions where these turn out to be constants. And so this is what we have. If we have a polynomial, p of x, and let's say we have a1x plus b1, a2x plus b2, well, this is going to be equal to, well, some constant a over a1x plus b1. In other words, just this factor plus b over a2x plus b2. And so this is a general formula we can use. So what will happen is we'll be given this. We want to break it down into this. Now, the problem is we're going to be given the factors, but we won't have a and b. We got to search for a and b. So that's going to be sort of the big task here. So let me get an example to work on. So what we're going to do is rewrite this as a over x minus 2 plus b over x plus 1. That's just how we break it out. Now what we want to do, a lot of the times when we work with rational functions, we want to cancel the denominators. So we want to multiply everything through by this denominator. So I'll do something like this to each term. Make sure you can see that on the camera. And then add b over x plus 1 and again. So we look at what cancels. Well, here we get some cancellation. Here the x minus 2 goes away, and the x plus 1 goes away. So what we have left we get a x plus 1 plus b x minus 2. So again, we're working with rational functions. Try to make life easier, get rid of those denominators, cancel those out. Distribute A, distribute B. And we're going to try to use comparisons to come up with a system of equations. So let me show you what that looks like. So we have this. I'm going to gather like terms on this right side. So I have some x terms. And then some constant terms. And remember, a and b are constants in this case. So let's factor out the x. Now let's take a look at things. Our claim by this equal sign is that both sides are equal. So that means this, excuse me, this 11 is going to be equal to this a plus b because the 11 has the x, a plus b has the x. So these two, they've got to be equal. So that's our first equation. Then we have the constant terms and a constant. So that means these constant terms, they've got to be negative 10. And this all comes from the fact that these two sides are equal. So that means the x terms need to be the same, and the constants, well, this constant and this constant expression, those need to be the same. All right. So what we can do is solve this system of equations. So I'm going to take this. I'm going to use substitution. I'm going to solve for a. So if I solve for a, I subtract b from both sides. And now I take this, I'll substitute it into this equation. Subtract 11 from both sides. And we get that. Now divide by negative 3. B is 7. All right. Now we need to find a. And recall that we had a plus b was equal to 11. Well, we know we know b is 7. Means a plus 7 is 11, or a equals 4. Subtract 7 from both sides. So what does this mean? Well, it means that original rational function, the 11x minus 10 over x minus 2, x plus 1, well, that's going to be 4 over x minus 2 plus 7 over x plus 1. So again, when you get to calculus, this could be really painful to integrate, but you can break it down into something like this, much easier to work with. Now there's different versions of this. And let me show you another one. So let's see here. Let's say you have this. Let's say we add these together. Again, I'm going to use that shortcut. You multiply across for the denominator. Cross multiply. Bring down the operator. Cross multiply. And then we're going to simplify in that numerator. Well, what we could do is we could maybe factor out an x plus 1. Do that. And we can see some cancellation here. Cancel an x plus 1. We distribute this through. Combine like terms. And we're going to get this. So what does this actually mean for us? Well, what it means is this. That 2x, if you think about what we started out with, we had 2 over x plus 1 plus 4 over x plus 1 squared. And this was now equal to 2x plus 6 over x plus 1 squared. Now, what we're going to be interested in, again, is the reverse. 2x plus 1, I'm sorry, 6. Well, it's going to be this. So once again, something that could be giving us some trouble integrating in Calc 1, we can break it down into something that's going to be a little more manageable. So in general, what we have is this. So if we have ax plus b squared, it'll be a plus b. And notice, and this is the part that's kind of maybe not expected, but we might think, well, it's going to be ax plus b and ax plus b, but it isn't. When we have repeated factors, we're going to get the factor and then its square. So let's do an example. So let's say we have this. Now again, the goal is going to be finding A and finding B. So we'll have A over x minus 1 plus B over x minus 1 squared. So again, we want to get rid of these denominators. So if we take x minus 1 squared, multiply through, this is what we're going to get. So we look for cancellations. X minus 1 squared, x minus 1 squared, that goes away. We'll lose this x minus 1 and we'll lose the square. We'll have an x minus 1 that remains. X minus 1 squared, x minus 1 squared, that goes away as well. So let's take a look. Well, this is what we have left. Let's distribute this through. So we've got our terms basically gathered. The x term has to match the x term, so that means A has got to equal 6. Then negative 11, this is the constant term, has to equal the constant expression. So negative A plus B is negative 11. Well, we've got A already. That just popped right out. So that's great. So that means negative 6 plus B equals negative 11. Add 6 to both sides. B will be negative 5. So what this says is this. Again, negative times 6 would make this turn into negative 6. Add this to both sides. You'll get that negative 5. So what do we have here? Well, this means 6x minus 11 over x minus 1 squared will be 6 over x minus 1 minus, because b is going to be a negative, x minus 1 squared. And there's our fraction decomposition. partial fraction decomposition. All right. So let's see here, a general formula that's kind of a version of this. If you have, so I'm just going to give you the formula for this one. But let's say it's not a factor, like ax plus b. Let's say it's a little more complicated. Instead of being ax plus b squared, let's say it's ax squared plus bx plus c. I'm just going to center my p of x here. Well, what this means, there's an ax plus b, and then ax squared plus bx plus c, plus a cx plus d, and then you have an ax squared plus bx plus c squared. So it gets a little more complicated. Let's see here. Let's do an example with one of these. They have one. There we go. So let's say we have this. So if we've got something like this, what we're going to do, break it down to ax plus b over x squared minus 2x plus 3 plus cx plus d x squared minus 2x plus 3 squared. So again, what we want to do, we want to multiply through by this denominator. So if we do that, it's going to be very similar to the example we saw before. And let's see, hopefully this won't get cut off. Oh, just barely. Barely is there. All right. Okay. So we look for cancellations. This one will lose a square. And then this will cancel and that'll cancel. Similar kinds of cancellations we saw in the most recent example. So again, x cubed minus 4x squared plus 9x minus 5, because its denominator completely canceled, then ax plus b times one of these, x squared minus 2x plus 3. And then again, the denominator canceled completely on this term. And so that's what we've got. So what we're going to need to do, we're going to need to distribute this through. So I'm going to multiply each of these by the ax. Check my multiplication here. Looks okay. All right, so far so good. Now we multiply each of these terms by the b. And now we gather like terms. So you have an ax squared, cubed rather, minus 2ax squared plus bx squared. And we have a plus 3ax minus 2bx plus 3b. Oh, I forgot. But still tack on the cx plus d. Don't want to forget that. So this means, let me gather like terms again. We got ax cubed. I can factor out the x squared here. And then if I combine this cx, factor out the x from these terms, 3a minus 2b, add that c there. And those are all the x terms with the x factored out. All right, and then we have a, for constant term, we have a plus 3b, of course we don't want to forget our d, plus d. All right, so let's take a look here, make sure this is all together. All right, minus 2b for the x, there's a 3ax and then a cx. All right, and then for the constant, the 3b and a plus d. Okay, well, so far so good. So now I want to compare terms. Well, we have an ax cubed and an x cubed. Well, this means a has to equal 1. Well, there we go. And then we have a minus 2a plus b for the x squared here. That's got to be equal to the minus 4 for the x squared there. Now we know a equals 1. So that means negative 2 times 1 plus b is negative 4. Negative 2 plus b is negative 4. Add 2 to both sides. If b is negative 2. Okay, good. I'm going to put that off to the side here. A is 1, B is -2. So now we got to deal with this x here. So we have a 9 here. We have 3a minus 2b plus c. That's for this x term. This has to equal that 9. Now we know a and b. A was 1, and b was -2. And so we find out that c is equal to 2. Lastly, we'll look at the constants. Constant, -5. Constant expression, 3b plus d. Well, we know what b is. B is -2. -6 plus d is -5. Add 6 to both sides. D is going to be 1. So we get D is 1. So what does this say? Well, let's look at the original problem. And x squared, let's see, sorry, x cubed minus 4x squared plus 9x minus 5 over x squared minus 2x plus 3 squared. And so this is going to be equal to ax plus b. So that's going to be 1x plus -2 over x squared minus 2x plus 3 plus cx plus d, or 2x plus 1, over x squared minus 2x plus 3. And we can clean this up a little bit. 1 times x is just x. When you add a negative, that's the same as subtracting. And so there we go. Oh, forgot. This needs to be squared. So there's our partial fraction decomposition. All right. So let me do another one, and you'll encounter this type of question from time to time. So let's say we have something like this. So what we're going to do, we're going to have to break this up like so. We'll have an a over the x, but then we'll have a b over the x minus 1 and a c over the x minus 1 squared. So what we're going to end up getting is we treat this sort of like the first example. There's a factor and a factor. So this one gets its A. This one would usually get its B. But what's really going to happen, since this is a repeated factor, we're going to treat it, we're going to break it down like a repeated factor. So we break them up, as we usually do. A over this, and then something over this, but because it's repeated, we got to do that thing where we have the factor and then the factor squared. All right. So again, we multiply through. We want to cancel these denominators. We multiply through by this. Oh, let me see. I'm sorry. Let me back up. A over x times oh, put the x in there. So again, we multiply through by this denominator, and we're going to look for cancellations. So for the A term, we lose the x. For the B term, we keep the x, but we lose one of the x minus 1s. The square goes away. And then for the C term, we lose the x minus 1 squared. And of course, for the original, or I'm sorry, the left side, we're going to lose the entire denominator. So what we're left with A times x minus 1 squared plus B times x minus 1 plus C times just x. So we're going to FOIL distribute, and we'll get distribute that x, and this would just be cx. Distribute again. And now let's gather like terms. So we still have our x squared plus 2x plus 7. Let's double check real quick. Yes. And so if we gather x squared terms, and then x terms, double check. And then one constant. Well, what we'll get, a plus b x squared, and then plus minus 2a minus b plus c x, and plus a. Now, when we compare this to this, the easiest thing to do, we have the constant expression, the constant, right away that tells us a equals 7. There we go. Now we have a plus b for x squared, and then coefficient of that invisible 1 for x squared. But we know a is 7. So subtract 7 from both sides. B is negative 6. I'm going to write this off to the side. So finally, I'm going to find C. So we have minus 2a minus b plus c is equal to, and then the x term is 2. Now we know a, and we know b. A is 7, B is negative 6. So negative 14, negative and negative is positive 6, plus C equals 2. Or negative 8 plus C equals 2. Or C equals 10. So what does this actually mean? Well, let's take a look. Take the original function we had here, x squared, well, what this will be equal to a over x, so 7 over x, b over x minus 1, so this is going to be a subtract 6, x minus 1, and then a plus c, or 10, over x minus 1 squared. All right, so there's your partial fraction decompositions. If you have any questions about that, let me know.